Yossef is a postdoc at Space Telescope Science Institute, but we are keeping the time because he's currently presenting to us from Israel, where it is quite late. So, Yossef, whenever you have a chance to share your slides.
Thank you. Yeah. Hi, everyone. I'm Yossef at Johns Hopkins Space Telescope. Second, I can share our screen. See my screen?
Yes, we see your screen. If you go into slideshow mode, you should be ready to go.
Okay, and
whenever you're ready.
Yes. Okay. So, hi everyone. Thank you, Gotham, Alex, and Bruno. It's a great honor to be here. I'm going to talk about calcium-rich supernovae and the original, actually, for the mechanism of calcium-rich supernovae. So this work done with by myself, Guy Peretz, Luke Desert, Wine, and Sylvia Tonin and Armin Rist. In general, or based on the observation elements composition of the supernovae, the observation channel actually, type 1a shows a lake of hydrogen, also no helium lines. It's almost no helium lines, but shows a strong silicon lines. There are two major identified classes of supernovae based on the physical methods by which they explode: thermonuclear or collapse. Stars that begin life with a mass below 8 solar masses will end their stellar evolution as a white dwarf with core of inert carbon-oxygen. Thermonuclear supernovae are believed to be the complete explosion of white dwarf, accumulating matter from an orbiting companion star, where the critical Chandrasekhar limit of the system is 1.4, or the white dwarf. The temperature of the white dwarf rises until a runaway thermonuclear reaction takes place that spreads across the interstar, and the radioactive decay of nickel to cobalt and then cobalt to iron power the supernova light output, producing a transient event which can be as bright as enter a galaxy. This is what we call the type 1a, and thermonuclear supernovae or core collapse, where the core collapse supernova is the explosion of massive star above 8 solar masses or 10 solar masses. Those supernovae come in a variety of observed subtypes depending on the composition of the progenitor star that explosion. And as you can see here, this is a zoo or tree of supernovae type 1a and type 2, and we're going to discover how calcium-rich related for type 1a or type 1b or c. We will see in this bench here, most of these supernovae striped envelope, the type 1c, type 1b, but it's out of focus on this talk. So here, as I said, calcium-rich could be a peculiar or subtype of type 1a or type 1b or c. And I'm going to focus on this transient as a subtype of type 1a. For example, as you can see here, the 91 BG or the calcium-rich. And if we look at the SKY survey, they give us almost 50% standard type 1a, and the other half is a peculiar type 1a. And what is the rate of calcium-rich type 1a? We will see later in this talk. And actually, there's many properties to define calcium-rich as a transient or as a supernovae. Many features, as of course, light curve, based on the observation, actually, spectra, the Philip relation, the nickel amount. As you can see, the intermediate luminosity for calcium-rich, it's below minus 16 mag, 16 half, and the nickel amount it's a small. This is the upper limit. As we know, it's 0.1 solar mass of nickel, and they come with very strong calcium emission lines, and the photosphere velocities is between 6 to 11,000 kilometers per second, and they are rapidly evolution to the unipolar phase, or in the B band between -15 to -14 magnitude, and the ejecta mass is something very important for calcium-rich properties. It's between 0.6 to 0.7, and for the host galaxies, mostly it's zero or elliptical galaxies. This is what we know. There's one supernova, observed supernova known as the PTF09DAV. It's not included in these types of galaxies. In general, the calcium-rich gap transient represent an emerging population of faint and fast evolving supernovae, and identified by their dominant calcium-rich line. And the light curve evolution actually characterized by the time scale and the peak luminosity faster and fainter than those of typical core collapse or type 1A of thermonuclear actually. One of the challenge for calcium-rich, it is not detection of any parent stellar population in late time imaging of the location of these objects. The remote location suggests that these transients arise from very old progenitor that may have traveled far away from the parent stellar population, or were possibly formed in this remote location. And I try here to say, like, maybe it could be a black hole merge, but we know they produced GRBs, or and the same with neutron stars black holes. White dwarf, we know maybe it gives rise to type 1A, and neutron stars white dwarf could be maybe. There's a few last decade research, they mentioned neutron stars white dwarf could be the progenitor of calcium-rich supernovae. We will see which one could explain this calcium-rich transient. Well, actually what is the progenitor of these subtypes supernovae? But it's until now it's still this progenitor remain unknown to date because many complicated or challenge both in observation and in theory/simulation. The successful channel include helium shell detonation in very mid of 80s by Woolsey. This idea developed until beginning of 2020, and we develop our model based on a helium detonation. I will explain in a minute what is helium detonation, and it could be double detonation of a helium shell on the surface of the central object. Mostly it's a white dwarf, and we will see if these white dwarf or neutron stars white dwarf could explain this peculiar type 1A or type 1BC as a calcium-rich supernovae. Before that, I wanted to just shed light on a specific white dwarf named hybrid white dwarf, which is this white dwarf formed through stellar evolution of single star or binary system, and there are several. In general, there are several types of white dwarf composed of carbon, oxygen, or oxygen-neon white dwarf correspond to the stellar evolution endpoints of intermediate and high mass star. And in interaction binary, each of the stellar component may fill its Rashlob overflow and may also evolve into a common envelope and be stripped of part of its hydrogen or helium-rich envelope during its evolution or on the main sequence stage or later on the AGB stage. That can give a rise to very low mass, VLM, below 0.45 solar mass. And you can see the first studies claimed by Abin and Titukov. In particular, wide dwarf of masses lower than 0.45 are typically through to be a helium wide dwarf formed through this channel. I mean by this channel, the binary interaction. And the hybrid, it's similar to the helium stellar evolution, but the complex binary evolution, it's a little bit different. When the most of the red giant envelope is removed, hydrogen shell burning is quelled and the helium core keeps growing and the star begins to contract. If the helium core is massive, the contraction will eventually trigger the helium again and the formation of CO core continuous, and the helium to CO ratio will then be determined by the specific detailed evolution of helium burning into CO. Actually, this is how the hybrid wide dwarf formed. We stay with a CO core with a helium shell, thick shell actually, and here just a plot of the log R and the mass of the wide dwarf, and here where the hybrid lay, and this is play a critical role for these wide dwarf explosion wide dwarfs. They lay between 0.36 to 0.75 solar masses, and this is could be as I mentioned, a key or critical key to explain some of these peculiar thermonuclear supernovae. But to estimate the rates and the delay time distribution of this hybrid, we used a population synthesis code named SIBA. Is a fast code for simulation binary evolution, and they can tell us that this hybrid wide dwarf, it could be similar to double degenerate wide dwarf rates. It's actually until it could give rise between 5 to 25 helium mass fraction in the wide dwarf, and that's what we need to succeed to explode or detonate a wide dwarf. So how we actually doing that? That before that, a critical physical process we need in general in type 1A or in peculiar type 1A is a detonation initiation with a Helium-CO or CO wide dwarf, as a detonation can be initiated in one of two ways, either directly from shock propagating into a reactive medium at a speed exceeding the Chapman-Jordan speed of the condition in the foil, or spontaneously through the preconditioned mix of a heated foil. So detonation in its simplest form is a shock that advises us supersonically into a reactive medium behind which a chemical or nuclear reaction proceed. So this is critical for follow the explosion of the system. So we follow Paluzzo and Fryer-Woolsey in the 80s and 90s. They considered the merger of wide dwarf black hole as a progenitor of long GRBs. They explore the dynamics of disk formation during unstable Rashlob overflow in circular orbits around the stellar mass black hole using SPH code, which with nuclear burning, and predicting the accretion power expected from the resulting disk. Metzger in 2010-2012 explore evolution of torus formed during a quasi-circular wide dwarf neutron stars black hole merger. Results showed that the nuclear reaction are important compared to the viscous heating, and that's the radially inefficient nature of these disks should result in a significant outflow. Recently, we, by myself, have reported two-dimension time-dependent simulation of the disk, including a physical equation of state, Helmholtz, and a coupled 19 isotopes and 13 nuclear reaction networks, viscous angular momentum transport, and self-gravity of the torus, and detonation are also reported. And that's what we need to get a transient. So how are we doing that? We use Flash. Flash is an AMR code, and we explore a wide range of conventional wide dwarf mergers. And as you can see, it's a map of density plot. Here, this is the Z direction. This is the R in cylindrical coordinate. In the central, you can see the hybrid wide dwarf, and the torus is a disrupted CO wide dwarf, where the CO wide dwarf is less than the central or the hybrid. And how we develop our torus, we check our equation by Stone in 99 by using SPH water oil code of SPH, and we can see what is the disruption between these two wide dwarfs give us. This is a few different view of the system. Here I can show the tumor instability of these systems because the regime of the mass of the hybrid, the ratio between the hybrid to the CO wide dwarf, it's between 0.8 to 0.9. And that's a little bit a challenge to relax the system with thick disk, and what is the surface density we need. And we check our 1D solution to the simulation, and you can see these stars. This is 3 different models. You can see the recent paper that we published, and the dashed lines, it's the same models with the surface density. And you can see this. Yes, and this is, thank you. This surface density, it's between 1D to the cylindrical coordinate, also the 2D flash simulation. It's give the same tumor stability, and we can start our simulation. And here, just a different view of the system in very late time. Here, we don't use just to check how the torus radius large. We use still in the averaging, using the averaging space density, and we see we get the same here as you can see here. This is the merge after time. This is the same, still the density evolution. Here the time, it's not in the second, it's a mistake. It's a viscous time scale, like actually half of the viscous time scale. And here I just show the density above 10 to 6, because all these density could be transferred to intermediate elements or nickel mass. And here what you can see, all these small points, it give us a nickel mass. And if we follow the flash simulation using 1D radius transfer code, and we compare our results to the observation, you can see how our model really fit the calcium-rich supernovae we compare to other known type 1a calcium-rich supernovae, and all these models give us a nickel mass below 0.1 solar mass, and the ejecta mass around 0.6, 0.5, and here the spectra in early time, and here the late time. You can see how it's fit the calcium emission lines from in the medium time. Actually, it's like 24 days peak. And if we trying to see where these models lay in Phillips plot, we can see our model really lay in the right regime of peculiar type 1a or calcium-rich supernovae. This is the population sentence of the hybrid white dwarf with a CO white dwarf. What we can explain of these peculiar type 1a, and this is my summary. I leave it, and I can take question also. Thank you. I can't hear anyone.
Thank you. Any
Yes.
questions?
Okay.
Kostya?
Yeah, hello, I'm Kostya Malanchev, postdoc here at UC. Thank you for your talk. How sensitive are your accretion disk models to the viscosity parameter, or do you model it without any viscosity?
Yeah, okay, it's a good question. Actually, yeah, we use our viscosity, and we found the viscosity. The viscosity we believe could explain this or give the same result between 0.08 to 0.1 to 0.08. This is the if we're going to smaller viscosity, we can't report detonation, but the evolution is similar, but without detonation. So the viscosity we use, it's 0.01. It gives us very nice results.
Thank you.
Same. Yeah.
I had a naive question. What radiation transport code did you use for the?
Yeah, it's the hello and sorry. So yeah, it's a good question. Also, I think I missed this part. I didn't mention. I used two. One, the supernovae code. It's open source code, and the second one is developed by Luke Desert. If you are familiar with it, it's I think it's have a very different strange name. It's GMFC code. It's a desert Luke Desert code. I don't think it's open source like supernovae, but we compare. Oh, the name is CMFGEN. It's a non-LTE radiation transfer code, but we compare our between both the supernovae code and the non-LTE code, and it's give the same volumetric light curve and spectra. Maybe a little bit the NLT much accurate or higher precisely. Yes.
Great. Thank you so much, Yossef. And thank you, Anirban, for answering that question. That's the perfect segue, in fact, into your own talk, Anirban. So whenever you're ready, could you please share your slides?